All right, I'd like to take you on a quick tour of the solar system, starting out with the sun. Let's take a look at this slide. And you already know this. There's a process going on in the interior of the sun. Of course, that's the fusion that generates all this energy. And we're converting hydrogen into helium. And then, so now the sun in its interior is about 60% helium. And think about what it used to be. I mean, the universe was originally 25% helium, so the sun has already converted a lot of hydrogen to helium in the processes that are going on in this nuclear fusion. Remember, the sun's 4.5 billion years old, so during that period of time, the sun has had plenty of chance to convert hydrogen to helium, and it's got another 5 billion years before it uses up all of that hydrogen. And then you have this convective zone on the outside of the sun, and that convective zone brings that heat to the surface. So lucky for us, we're getting this heat that's generated by fusion in the center being carried out to the exterior of the sun, where you know, the Earth can take advantage of it, and the other planets, of course, too. Now, I think one of the things that's very interesting about the sun is that it has a lot of metals in it. In fact, it's as rich in metals as any of the stars out there in our galaxy. And what does that mean? Well, you should already know after our discussions on supernovae and also red giants, is that that's the source of any elements larger than helium. So we must have had supernovae out there blasting away and penetrating elements penetrating into the cloud that would collapse to form our solar system. We call that cloud the solar nebula, and it must have been permeated, or it must have had these supernovae blasting out these elements that were created in the supernovae, and all of them going through the solar system. And in fact, as we'll find out later, it might have been a supernovae close by that caused the solar cloud, the solar nebula, to collapse, which is kind of interesting in itself. The sun's temperature in the interior is 15.7 million degrees Kelvin, so it's incredibly hot. I don't know, it's kind of unimaginable numbers. And then on the surface, it's just a mere 5,778 degrees Kelvin. Yeah, right. Anyway, I do want to show you something I think that's interesting. Look at this video of the sun and the solar flares. These flares are going out thousands of miles into space, and they can be a potential danger to the Earth. If they're directed towards the Earth, they can the materials coming from them can slam into our magnetic field. We'll talk more about how the magnetic field of Earth protects us from the solar wind and flares coming from the sun, but it can still do damage when some of these flares point towards Earth, and satellites have been knocked out by them. We actually have satellites now close to the sun that are monitoring solar flares, so they can radio back to Earth and say, hey, you know, time to shut down the satellites while this flare storm goes through. So I think pretty spectacular video there. The sun has a magnetic field. That convection inside the sun is creating a magnetic field, and you know where this magnetic field lines are concentrated when they come out of the sun or go into the sun, it tends to inhibit the convective cells in the outer sun from coming to the surface, and so those areas become cooler, and that's what causes sunspots. Now, the sunspots have come and gone on a pretty regular basis of 11 years, and you can see in this bottom diagram the sunspot activity. The patterns are basically about 11 years, but you can see back in the 1600s and early 1700s that the sunspots practically disappeared. So we don't know exactly why, but we think we we know that the sun was producing less energy at the time that the sunspot activity dropped in the 1700s. And that resulted in something called the Little Ice Age in Europe and North America, resulting in, the reason it was called that was because there were very, very cold temperatures during that period of time. And on top of all that, of course, this is just about the time that the Puritans end up coming to North America. They arrived in 1620. By the 1640s or so, things were getting pretty cold. As you can see, the minimums going there. And you always hear about the miserable winters that the early settlers had. Maybe you've heard about Roanoke, Virginia, and the Lost Colony and that sort of thing. So survival was very difficult, partly because of this cold weather that was hammering well, New England, North America, and also over in Europe. One of the things that I should mention is that the solar wind is kind of the product of all of the things that are happening. It's the sloughing off of material from the sun, and it permeates through space, and it literally is a wind of particles. They're mostly electrons, protons, and alpha particles. And you may remember that alpha particles are made up of 2 neutrons and 2 protons. So they're rather large, and they blast through space, and they hit the planets. Thank God we have a magnetic field which protects us against the solar wind, or we might not have life the way we know it on Earth, that's for sure. One other thing to mention about the sun is that up until about 2.5 billion years ago, it was approximately 75%, I should say, it turned out the 75% of the energy that it turns out today. So it was much colder prior to about 2.5 billion years on the planet. And you know, it's kind of interesting, the water on Earth would not have been able to be liquid at the amounts of energies that were produced by the sun during that time. The only thing that saved us and allowed liquid water to be in oceans was probably the fact that we had an atmosphere that could create a greenhouse effect and give us the heat that we needed. We had a magnetic field, fortunately too, that surrounded Earth and protected that atmosphere. So we are lucky in that sense. Well, let's go on to Mercury. Talk a little bit about Mercury. Mercury is the planet closest to the sun. It's the smallest planet, and it has no moons. What else do we know about Mercury? Well, we know that Mercury is pretty hot, being close to the sun. We also know, if you can probably tell this from looking at the outside of the planet, that it's been bombarded like mad with, it's pockmarked with craters. And I am going to refer to something called the late heavy bombardment, and I'm going to refer to that a lot. We know from studying the moon, and we dated the rocks on the moon, that between 4.1 billion years ago and 3.8 billion years ago, we had this period of heavy bombardment of the moon by meteorites. And we think that it's all related to this junk that was flying around the solar system and being swept up by the planets. But until it got all swept up, there was a lot of impacts, a lot of bombardment. So we can, because of our work on the moon, we can carefully date that period, and we see remnants of the or what we think is the late heavy bombardment period all over the solar system. And really, we'll see it on Mars, we'll see it on some of the moons out there, so keep that in mind. And I can tell you with some confidence the fact that this has got craters all over. It means that probably nothing has happened much on its surface since about 3.8 billion years ago, when most of this cratering was done. Another thing, take a look at that shot down in the bottom of the picture. That's the interior of Mercury. Mercury has a mantle and a core, a mantle, and a crust. And I'm going to refer to this later on when we're talking about the planets as differentiated. What probably happened is that Mercury was all melted at one time by all of this bombardment, and it formed a molten magma out of Mercury, either partially molten or completely molten, and it gave a chance for at the high temperatures, when the molten rock began to cool, the first thing that cooled out of it was iron, and then some nickel, a little bit of nickel, a lot of iron, and this iron sunk to the center because it's denser than the liquid, and it formed the mantle of Mercury. We see the same thing happening on Earth and the Moon and a lot of the other planets. So this is what I mean by differentiation. The next set of minerals that cooled out of the magma, those two minerals would be primarily olivine and pyroxene, and they went to form the mantle. And then either what was left over formed the crust, or it could be that you had some partial melting of the mantle, and magmas came to the top and formed minor flows. But for the most part, most of Mercury formed about 3.8 billion years ago. So we know then that this differentiation looks like it occurred prior to 3.8 billion years ago. So again, when I refer to differentiation, or when I refer to the late heavy bombardment, you'll have an idea of what I'm talking about. The next planet out from the Sun is Venus. This is a false color image of Venus. There's a reason for that, and that is that Venus is covered in carbon dioxide. The carbon dioxide concentration of Venus is 96%. And we have what's called a runaway greenhouse effect on Venus. It is the gases are trapping heat from the sun via this greenhouse effect, and the temperatures are the hottest on the surface of Venus, the hottest of any planet in the solar system. That includes Mercury, which is closer to the sun. Get this, Venus has 735 degrees Kelvin, or 462 degrees centigrade on its surface. So if you could survive on its surface from the pressure, which you couldn't, then you'd burn up. So not a hospitable place at all. In fact, the atmosphere is 92 times denser than that of the Earth. So 92 atmospheres on planet Venus, you would die there. One of the things that we did do, though, we sent a spacecraft called Magellan to Venus, and it had a radar that could penetrate the atmospheric clouds and look at the surface of Venus, and that's why you're seeing this false color image here. It was made by Magellan. And one of the cool things we found out was that Venus is covered with volcanoes and volcanic activity. It's got volcanic plains, and it's got, let's see, I think about 167 large volcanoes greater than 100 kilometers, big volcanoes. And you can see one in this slide, the Mott volcano. And we've got some evidence that they may be active. Look at this diagram. I'm plotting sulfur dioxide I'm not plotting, the guys that did this article plotted it. They're plotting sulfur dioxide in the atmosphere. They started doing that about 1978, and you can see that we went from a peak in 1978, it continually dropped off until the 1990s. Then about 1991 it went up a little bit and then dropped off, and then we didn't see anything in the atmosphere until about 2006, it looks like. 2006, the sulfur dioxide jumped up precipitously, so to speak, and then it's now been going down. And sulfur dioxide is a typical product of volcanoes, and it's so it looks for all the world like we've got volcanic eruptions on the surface of Venus. And we can't prove that, but certainly this variation in sulfur dioxide in the atmosphere would suggest that there's some active eruptions going on Venus. So it looks like it's not a dead planet. It certainly it is differentiated, and it's got a slight magnetic field, not a great magnetic field. It's probably due with the solar wind interacting with Venus's ionosphere to generate, a pretty pathetic magnetic field.